You start, sir.
Okay. Good morning, students, and good morning, everyone. So today, and in the last class, we have proved some identities, and today it is the 7th class, binomial theorem. 7th class, we shall prove some more problems based on the identities of the coefficients. So problem number, the serial number is 17. Find the sum of the following. Find the sum of the following. 3C0 plus 6C1, 6 into C1 plus 12 into C2 plus so on, plus 3 into 2 to the power of n Cn. 3 into 2 to the power of n Cn. Let us solve this. Solution. Consider LHS, or we have to find the sum of this one. So we don't need to prove this one. So we'll consider this expansion. If you look at this one, we'll write this again. 3C0 plus 6C1 plus 12C2 plus so on plus 3 into 2 to the power of n Cn. So what is common throughout? Look at these. The common term is 3. Let us take 3 in common. So this will be equal to 3 into C0 plus 2C1, 2 into C1 plus 4C2 plus so on plus 2 to the power of n Cn. This can be written as 3 into C0 plus 2C1 plus 4 can be written as 2 square into C2 plus so on plus 2 to the power of n Cn. So this will be equal to 3 into, so we can write this as C0. I'm rewriting this again. I'm writing C1 into 2 plus C2 into 2 square plus so on plus Cn into 2 to the power of n. So this is equals to, according to the identity, we have 3 into, you can write this as 1 plus 2 whole power n. So this will be equal to 3 into 3 to the power of n. So this is nothing but 3 to the power of n plus 1. So we have used the identity 1 plus x whole power n. The formula for this one is 1 plus x whole power n. So what is that 1 plus x whole power n? 1 plus x whole power n, since 1 plus x whole power n is equals to C0 plus C1x plus C2x square plus so on plus Cn into x to the power of n. We have used this identity and proved the result. and prove the result. C0 plus C1x plus C2x square plus so on Cn x to the power of n, where x is equals to 2. 1 plus x whole power n, where x is equals to 1 plus 2 whole power n, which is 3 to the power of n, into 3 to the power of 1, which will give you 3 to the power of n plus 1. We shall see one more problem. Problem number 18. Using binomial theorem, one more type of problem. Using binomial theorem, prove that 50 to the power of n minus 49n minus 1 is divisible by 49 square is divisible by 49 square for all positive integers n. For all positive integers n. Let us see the solution. So using binomial theorem, you have to prove that 50 to the power of n minus 49n minus 1 is divisible by 49 square for all positive integers n. Now consider 50 to the power of n minus 49n minus 1. So we can write 50 as 49 plus 1 whole power n minus 49n minus 1 as it is. Now, if you look at this one, this is in the form of x plus a whole to the power of n. We can use the identity x plus a whole to the power of n. Which identity? X plus a whole to the power of n. X plus a whole to the power of n is nothing but nc0 x to the power of n a to the power of 0 plus nc1 x to the power of n minus 1 a to the power of 1 plus nc2 x to the power of n minus 2 a square plus so on plus nc n x to the power of 0 a to the power of n. If you compare with this 49 plus 1 whole to the power of n, here x will be 49 and a is equals to 1. Comparing 49 plus 1 whole to the power of n with x plus a whole to the power of n. We shall expand this one, which is equals to nc0 49 whole to the power of n into 1 to the power of 0. So all these will become 1 because a is 1. 1 raised to anything is 1. nc0 49 whole to the power of n plus NC1 49 whole to the power of n minus 1 plus NC2 49 whole power n minus 2 plus so on plus NC n minus 2, I'm writing previous terms, into 49 whole square plus NC n minus 1 into 49 whole power 1 plus NCN 49 whole power 0, and at the end what do we have? Minus 49n and minus 1 as it is. Minus 49n minus 1. Now we shall continue to the next step. So this is equals to (49 whole to the power of n) plus NC1 into 49 whole to the power of n minus 1 plus NC2 into 49 whole to the power of n minus 2 plus so on plus NC n minus 2 49 square plus n into 49 plus 1 into 1, and again we have minus 49n minus 1. Look at the previous term. We have NC0. NC0 is 1 and NCN is also 1. And if you look at this term, NC n minus 1, look at this term NC n minus 1, we can use the formula NC n minus 1 is equals to NC n minus of n minus 1, which is equals to NC 1, which is nothing but n itself. So the previous term, this was NC n minus 1. So we have used the formula NCR is equals to NC n minus R. So based on this formula, we have got NC n minus 1 is equals to n. Then the next step, look at this one. These two terms will get cancelled. This is 49n, n into 49 is 49n and minus 49n, and 1 will get cancelled because in the previous term NC n is 1 and 49 whole to the power of 0 is 1. So we've written 1 into 1. So this can be written as (49 whole to the power of n plus NC1 into 49 whole to the power of n minus 1 plus NC2 49 whole to the power of n minus 2 plus so on plus NC n minus 2 into 49 whole square. This is a term left. These terms get cancelled. Then this is equals to, we shall take 49 square common. 49 whole square common. Then we can write this as 49 whole to the power of n minus 2. If you take 49 square common, this will become 49 whole to the power of n minus 2. Then plus NC1 49 whole to the power of n minus 1 will become 49 whole to the power of n minus 3. In other sense, you can also do multiply and divide by 49 whole square. This will become 49 whole to the power of n minus 3 plus NC2 49 whole to the power of n minus 4 plus so on plus NC n minus 2. So this is nothing but 49 whole square into a positive integer. This is a positive integer. Hence, (50) to the power of n minus 49n minus 1 is divisible by 49 square for all positive integers n. Just look at the solution once again. So what we have done, the question was using binomial theorem, prove that 50 to the power of n minus 49n minus 1 is divisible by 49 square. So we took 50 as 49 plus 1 and we've expanded this using x plus a whole power n. So this is a standard expansion of binomial theorem. And here, if you compare these two, x plus a whole power n and 49 whole plus 1 whole power n, we have x is equals to 49 and a is equals to 1. And using this identity, we shall expand this and simplify. And then at the end, you get 49 square into a positive integer, which is divisible by 49. So you can say that 50 to the power of n minus 49 minus 1 is divisible by 49 square. Okay, we shall do one more problem. If 1 plus x plus x square whole to the power of n is equals to a naught plus a1x plus a2x square plus so on plus a2n x to the power of 2n. Then prove that we have 4 bits under this. Prove that first one is A0 plus A1 plus A2 plus so on plus A2n is equals to 3 to the power of n, and the second one is A0 plus A2 plus A4 plus so on plus A2n is equals to 3 to the power of n plus 1 divided by 2. The third one A1 plus A3 plus A5 plus so on plus A2n minus 1 is equals to 3 to the power of n minus 1 divided by 2. And the fourth one A0 plus A3 plus A6 plus A9 plus so on is equals to 3 to the power of n minus 1. So we shall solve these one by one. And the first one, before getting on to the first one, we shall take down the solution. So we have what is given. We have 1 plus x plus x square whole to the power of n is equals to A0 plus A1x plus A2x square plus so on plus A2n x to the power of 2n. This is given. 1 plus x square whole to the power of n is A0 plus A1x plus A2x square plus so on A2n x to the power of 2n. I've written this. So now, let us consider this as equation 1. Put x is equals to 1 in equation 1. What do we get? Put x equal to 1 in equation 1. We get 1 plus 1 plus 1 whole to the power of n is equals to A0 plus A1 as x is equals to 1, A2 plus so on plus A2n. X is 1, 1 square, 1 to the power of 2n. So this implies, I'll write the RHS term first, which is A0 plus a1 plus a2 plus so on plus a to n is equals to 3 to the power of n. 1 plus 1 plus 1, which is 3 to the power of n. Let us consider this as equation 2. Now put x equal to -1 in equation 1, we get one. X is equals to -1, it will be -1 plus -1 whole square will be 1 whole to the power of n. If you look at this one, 1 -1 plus -1 whole square is plus 1 whole to the power of n is equals to a0 a1 into -1, which will be minus a1 plus a2 into -1 whole square is positive plus 1. Again you will have minus term and so on plus a to n. -1 whole power to n is positive again. So this implies, I'll write the RHS first, a0 minus a1 plus a2 minus so on plus a to n is equals to 1. Let us consider this as equation 3. If you look at this one, 1 minus 1, these two get cancelled, 1 to the power of n will give you 1. So based on these three equations, we shall solve to prove the points. So the first point, what is the first thing you need to prove? To prove that a0 plus a1 plus a2 plus so on a to n is equals to 3 to the power of n. So if you look at this one, from equation 2, we have, if you look at this one, so this is already the first proof, first point proof. a0 plus a1 plus a2 plus so on is equals to 3 to the power of n. We have, so this is already proved. We have a0 plus a1 plus a2 plus so on plus a to n is equals to 3 to the power of n. Now we shall solve the second one. We shall prove the second one. Now we'll add 2 and 3. Adding equation 2 and equation 3. Shall see what do we get? We get, what is the equation 2 we have? a0 plus a1 plus a2 plus so on a to n is equals to 3 to the power of n, and equation 3 is a0 plus minus a1 plus a2 minus so on a to n. If you look at these two terms, if you add these two terms, a naught plus a naught will give you 2a naught, and a1 will get cancelled, a3 terms will get cancelled, the alternate terms will get cancelled. So this will be twice. A naught plus a naught will be 2a naught, 2a2, and so on. So we shall write the resultant. Adding 2 and 3, we get 2a naught plus 2a2 plus, we'll write one more term, 2a4 plus so on plus 2a to n is equals to, on the RHS you have 3 to the power of n, and the other term is plus 1. We have 3 to the power of n and 1. So 3 to the power of n plus 1. This implies what is common? 2 is common throughout on the LHS. So you can write this as 2 into a naught plus a2 plus a4 plus so on plus a to n is equals to 3 to the power of n plus 1. We shall take this 2 to the RHS. Then this implies a naught plus a2 plus a4 plus so on plus a to n is equals to 3 to the power of n plus 1 divided by 2. If you look at the second proof, it will be a naught plus a2 plus a4 plus a to n is equals to 3 to the power of n plus 1 by 2. We have proved this one. We shall see the next one. So we got the second proof. And the third one, we shall subtract this. We shall subtract 3 from 2. In other sense, 2 minus 3 implies. So we shall subtract these two. If we subtract, a naught minus a naught will be cancelled. A1 minus of minus a1 will be 2a1. So we'll get 2a1, and these two terms will get cancelled, and 2a3. In other sense, we'll get the odd terms, a1, a3, a5, and at the end these two get cancelled, and the term before this will be a2 n minus 1. We shall see the resultant. And the third one, subtracting equation 3 from equation 2, what do we get? We get 2a1 plus 2a3 plus so on. We'll write one more term better, plus 2a5 plus so on plus 2a 2n minus 1 is equals to 3 to the power of n minus 1. So we get 3 to the power of n minus 1. So this implies, take 2 common, it will be a1 plus a3 plus a5 plus so on plus a2n minus 1 is equals to 3 to the power of n minus 1. This implies if we take this 2 to the RHS, then it will be 3 to the power of n minus 1 by 2. So this implies A1 plus A3 plus A5 plus so on plus A2n minus 1 is equals to 3 to the power of n minus 1 divided by 2. So this is the proof for the third bit. If you look at this one, A1 plus A3 plus A5 plus so on, A2n minus 1 is equals to 3 to the power of n minus 1 by 2. You got the same thing. Let us solve the fourth bit. The fourth bit is a little bit different. We shall see the proof. To prove that, what do we need to prove? Prove that A0 plus A3 plus A6 plus A9 plus so on is equals to 3 to the power of n minus 1. 3 to the power of n minus 1. Now, if you look at the second equation we got, we'll try to consider this second equation, A0 plus A1 plus A2 plus so on. A2n is 3 to the power of n. From equation 2, from equation 2, we have A0 plus A1 plus A2 plus so on plus A2n is equals to 3 to the power of n from equation 2. Now put x equal to omega, x equal to omega in equation 1. In equation 1, what do we get? In equation 1, you have to put x equal to omega. If you look at the equation 1, it is 1 plus x square whole to the power of n is a0 plus a1x plus a2x square plus so on a2n x to the power of n, which is given in the question. So if we have to put x equal to omega, it will become 1 plus omega square whole to the power of n is equals to a0 plus a1 omega a2 omega square plus so on a2n omega to the power of 2n. We shall simplify further. So this is equals to, put x equal to omega in equation 1, we get 1 plus omega plus omega square whole power n is equals to a0 plus a1 omega plus a2 omega square plus, we'll write one more term, a3 omega cube plus so on plus a2n omega to the power of 2n. This implies, we'll write the RHS terms first, a0 plus a1 omega plus a2 omega square plus a3 omega cube plus so on plus a2n omega to the power of 2n is equals to, get 0. On the RHS we get 0. And let this be equation 4. And since can write it as since 1 plus omega, we all know that 1 plus omega square is equals to 0. So we got fourth equation. Now put x equal to omega square in equation 1. Similarly, we'll try to put x equal to omega square in equation 1 and we'll see what we're going to get. We get, put x equal to omega square in equation 1, we get 1 plus omega square plus omega to the power of 4 whole to the power of n is equals to a naught plus a1 omega square plus a2 omega to the power of 4 plus a3 omega to the power of 6 plus so on plus a2n omega to the power of 4n. So we have considered x is equals to omega square. So this implies, we'll write the RHS first, a naught plus a1 omega square plus a2 omega to the power of 4 plus a3 omega to the power of 6 plus so on plus a2n omega to the power of 4n. Again, this is equal to 0. Since you can also say that since omega cube is 1 and 1 plus omega square is 0. If you look at this one, we'll write this one. If you look at this, we have 1 plus omega square plus omega to the power of 4. This can be written as 1 plus omega square plus omega cube into omega. Omega to the power of 4 can be written as omega cube into omega. So this will be 1 plus omega square plus omega. We can rewrite this as 1 plus omega square, which is equals to 0. So the LHS is 0. That is what we've written. Let us consider this as equation 5. Equation 5. Now adding equations 2, 4 and 5, we get 3 into a naught plus a1 into 1 plus omega square plus a2 into 1 plus omega square plus omega to the power of 4 plus a3 into 1 plus omega cube plus omega to the power of 6 plus so on plus a2n into 1 plus omega to the power of 2n plus omega to the power of 4n. On the RHS we get 3 to the power of n, and we shall simplify this further using these identities. Then we get 3a naught plus a1 into 0 plus a2 into 0. Since 1 plus omega square is 0, plus we get a3 into 3 plus, because omega cube is 1, we get 1 plus 1 plus 1 plus so on is equals to 3 to the power of n. So this implies we have 3a naught plus 3a3 plus, we'll write one more term, we'll get 3a6 plus so on is equal to 3 to the power of n. So we take 3 common, which will be 3 into a naught plus a3 plus a6 plus so on is equals to 3 to the power of n. So this implies if we take this 3 to RHS, we'll have 3 to the power of n by 3. So this will be a naught plus a3 plus a6 plus so on is equals to 3 to the power of n by 3, which is equals to 3 to the power of n minus 1. If you take this 3 to the numerator, it will be 3 to the power of minus 1, and this will become 3 to the power of n minus 1. And we have the fourth proof, fourth identity, or the fourth point proof, which will be a naught plus a3 plus a6, the other term will be a9, which is equals to 3 to the power of n minus 1. Okay, so we shall continue further in the next class. Thank you, ma'am. Thank you, sir. Thank you, madam. Thank you, sir.